In this video, we're going to look at X-ray crystallography. Now, let's imagine that you have a solid in front of you and you want to know how the atoms are arranged in that solid. What can you do? Well, there's an experimental technique that you can use that is called X-ray crystallography. And this is how scientists determine, in a solid, in proteins, how are the atoms or molecules actually arranged. Now, this will only work if the solid you are looking at is in a crystalline structure, as seen in the snowflake. And crystalline just means long-range order, or you have a pattern that's repeating over and over and over again. In general, what you do with X-ray crystallography is that you shoot a crystal with an X-ray. The X-ray will bounce off the crystal and you'll collect that like on film. Based on how the light bounces off, we can use a computer and determine, okay, if I get a refraction pattern that looks like this, the crystal must have looked like this. And this is actually how we discovered that, or one of the ways we discovered that DNA is a double helix. Here is the diffraction pattern of DNA, and an X-ray crystallographer can look at this and easily determine, oh, this has a helix structure. Now, to understand how X-ray crystallography works, we have to first remember how light works. So remember, light is a particle and a wave, and here we're worried about the wave characteristic of light. In light, if you have two light waves, they can either be constructive or destructive. Constructive interference is when the troughs and the crests line up in your light waves, and when they combine together, they'll make an even bigger wave. While destructive interference, thank you Java, destructive interference is when your crests and troughs are not aligned. So here we have, or rather the crests and troughs are aligned for the different waves. Well, I mean by a crest is aligned with a trough. Let me just say that clearly. You have a crest aligned with a trough and they'll add together and they'll cancel each other out and make a line, basically no light left. Now, the only way we can determine the atomic structure of crystals is if they have constructive interference. And crystalline solids will cause both constructive and destructive interference to happen. But we're really only worried about the constructive interference because the constructive interference is what we are capturing when we're measuring the light bouncing off the crystals. So let's look at some of the math of this constructive interference. So we're going to think of a very simple crystal. We have atoms that are in two different layers, so layer 1 and layer 2. These two layers are separated by a distance we're going to call d. Now let's say that we take these layers and we shoot it with light, and these lights have the same wavelength and they're going to bounce. So let's say one of the lights bounces off our first layer, ray 1. The other light bounces off our second layer, ray 2. All right. Now, these lights are going to travel different distances to hit their atoms. That difference is this path difference, and it's equal to 2a. So a is just our variable here. And so our criteria for getting constructive interference is the wavelength of light we used multiplied by any integer, so 1, 2, 3, 4, 5, 6, 7, must equal to a, which is the path difference of our light waves hitting the crystals. If this criteria is met, then these wavelengths will add up together, have constructive interference, and we can measure that, or we can capture that. Now, we can actually use trigonometry here to determine when constructive interference will happen based on this angle of reflection. You see here, the lights, when they hit the atom, they actually have an angle between the light coming in and our plane here. And so constructive interference happens when the sine of our angle, our theta here between our light and our plane, is equal to a, which is related to the path difference, divided by d, which is the distance between these layers. or A, the difference between the paths must equal d sine theta. And we combine this with our previous equation to get what's called Bragg's law. The wavelength of light we use multiplied by an integer will create constructive interference if it's equal to 2d sine theta. Or distance equals n theta divided by 2 sine, or n lambda rather, divided by 2 sine theta. So what actually happens is that you have a crystal and you're going to be rotating it 360 degrees. And as you rotate it, this angle will change. And you're going to have your light bouncing off. And by rotating it, you're going to make sure that you can capture every single instance of constructive interference in that crystal. And by measuring that, you can use a computer to calculate, okay, what atoms were in that crystal to get the pattern of light bouncing off that we saw in the experiment. And it's very high-level physics stuff to figure that out beyond this class, but we're just going to touch on the basics of X-ray crystallography, which we did in this video. And so that's it for this video, and I will see you in the next one.